Hello. Today I'm gonna demonstrate to you the technique which I just put together, um, which I modified from the cellular automata to generate natural-looking caves. So this is the end result. I code in Python and I use Pygame to render it. I think it looks kind of good. Well, you see, there's like these little sections that may look unnatural, but I think it's good enough, and actually it's perfect. If you're making like a rough like dungeon game like me, and I think it's kind of a great layout because it would look more like ruins and stuff, and would make space for certain structures unique and interesting. So the way that I do it is that I'm going to implement the regular technique of cellular automata, which you can check out a video in the description of how it works. So first I'm gonna, why is this color not working? First, the way I use it is that I separate the world into 13 by 13 chunks. No, wait, no, it's 32 by 32, sorry, mispronunciation. 8 32 by 32 chunks, and I use cellular automata in each and every one of the chunk separately, and then I use my random special technique that I just thought of to connect them all together and make it look more coherent, like an actual cave system, instead of a few disjoint, discrete, well, chunks. So, step one. Right. Step one is that we're going to generate a bunch of random cells, right? Here I'm using blank air for the walls, and these for the air pockets, the airs. And we're gonna generate it with a specified density, which is the walls to air ratio. Currently my density is at 60%, so it's gonna be a 60% chance that a cell is a wall, and 40% chance that it's an air block. And step two, we're gonna run this to a cellular automata. Like a cellular automata simulation to generate caves, right? Caves like this. The usual problem with this is that you're gonna have these little pockets right there and some huge one, but disjoint caves. What we want, I'm not gonna go in depth with how this function or this algorithm work. You could Google it up. There's tons of great resources, definitely better than mine, that could explain it. So let's just say this is our finished product of the cellular automata. After parsing it through the simulation, we're going to end up with these capes, for example. What we want is that we're going to want to connect the huge parts together and leave out the small parts. So the way I leave it out is just as simpler as the way other YouTubers do it and other coders. The basic way, the standard procedure is we're going to run a sort of algorithm, a recursive function, to mark out all of the regions, right? Gonna mark out all of these regions. That's what we're gonna do. In this specific example, I'm just gonna say this is region 1, region 2, 3, 4, this is 5, and this is 6. what we want is that we want to get rid of region 2, 3, and 6 and 5. Sorry. So we're gonna check if the total amount of cells, right? The total amount of cells in region I is less than a certain threshold, then we want to get rid of it, right? But if it's bigger than that threshold, then the standard procedure to do it would be to mark out all of the corner blocks, right? All the corner blocks of this. And we're going to find out which the sum of the distance from all corner blocks of this to each and every one of these corner blocks of all of the other regions, right? We're going to run it many times, and we want to check what is the minimal distance from region I to region J, right? We want to find out all of the minimal distance between one given room, right? Which room is the closest to that room, and we're going to achieve it by this way. And we're going to find the minimal sum of distance. So which room has its distance from each and every corner piece of this guy, which is the minimal, right? That's what we want. Of course, because the amount of corner cells vary, we're going to take the average of it, and we're going to find the minimal one, and we're going to connect those two rooms. And to ensure connectivity throughout all of the rooms, we're going to mark the biggest room as a center room, and we're going to try to form connections from, let's say this is a center room, right? We're going to try to form all the connection to this room either through a median room, like for example, if this 6 is connected through 4, which is connected to 1, then we say that room 6 is also indirectly connected to room 1, right? So yeah, that's the usual algorithm. But in my case, which I think can work well for a lot of you guys, instead of doing this, what I do is that, look, because my chunk size is small, I just do a measly a square check, a square scan, as I call it. I take a model, like a 3x3 square, and I'm going to run it through all of these. Right? I'm going to scan all the 3x3 square that is available in this 32x32 area. And if I detect that there are more than equal to 2 cells belonging to different regions, what I'm going to do is that I'm going to draw a line through the center of this 3x3 squared. That way, what we are going to achieve is that these are going to be connected, and no matter where those 2 cells of the 2 different regions are, they are definitely going to be connected by this middle bridge here. So most of the time this is going to work, and it is going to connect the whole 32x32 board together. But of course there are a few trivialities that doesn't get connected. In this case everything is connected, so that's good for us. But sometimes it doesn't work, and in that case I just get rid of the thing as a whole, because it would be a waste of computational time and space to check every individual rooms. It takes too much time and it's trivial. After that, this is where I think I'm the most fond of this algorithm. What I'm going to do, now we have a result of a cave system that looks somewhat resemble this, right? And what I'm going to do, that I'm going to mark, right? I'm going to mark all of these cells here. And I'm going to make a list of these cells with their respective directions. And if we generate this chunk here, then instead of randomizing all of the cells, I am going to first put these little extension, these buffer air cells into it first, then we randomize it. That way, it's going to ensure that we have an increased percentage of a cave that is linked to this little extension, this buffer part right there, which is going to be better for us for a more coherent cave system. And we can double down on this algorithm by ensuring that all of these cells here are going to be wall cells. That way, there's going to be no cave system that leads to a dead end of this chunk. So you can see this very clearly in my program. You see, I already preliminarily placed these little air cells here after generating this chunk. I've already placed these there. So that way, it's going to ensure that there's going to be a cave system of this cell. Of this chunk. It's definitely going to connect to this guy. Of course, this is not a 100% guarantee, as you can see, like this here and many other places. The caves aren't connected, but that's fine because that's only a really trivial composition of all the possibilities. And even more, it makes so that it would be way more natural cave system that there are dead ends. But doing it this way ensures that the probability of a dead end is lowered, which is of course good for us for a more coherent cave system, as I've mentioned a million times. Anyways, thank you for listening to my stupid presentation or whatever you call it. It's just a random, well, thought process of mine that came up with this algorithm modified version. I don't think anyone is gonna make this far anyways, but thank you for listening to my last two brain cells in my brain.